On the morning of June 2nd, 2025, tourists hiking the slopes of Mount Etna heard a sound that made their blood run cold. Not the familiar rumble of magma churning deep below, but something sharper, more immediate. A crack, then another. Within minutes, the volcano's southeast crater began to disintegrate from within, its northern flank collapsing in a cascade of superheated rock and ash. A pyroclastic flow tore down the mountainside at speeds that gave hikers mere seconds to react. Some ran, others stood frozen, cameras still rolling as a mushroom cloud of volcanic debris rose 6.5 kilometers into the Sicilian sky, nearly twice the height of the mountain itself. By the time the tremor subsided, aviation authorities had issued a red alert across the region. Tourists who'd been at the summit minutes earlier were now scrambling down access roads, their guides urging them forward as the mountain continued to shudder beneath their feet. One witness described it as hearing the earth itself crack open. For those watching from the coast of Catania, 25 miles to the south, the eruption looked biblical, a towering column of ash and fire rising from Europe's most active volcano. But what unfolded that June morning wasn't just another eruption, it was a warning. Scientists monitoring Etna's behavior had seen this pattern before, buried in the geological record, and what they discovered in the aftermath has left them racing against time to answer a single haunting question. Is Mount Etna preparing to collapse into the Mediterranean Sea? The southeastern flank of Mount Etna is on the move, not in the dramatic, catastrophic sense, not yet, but in a slow, relentless slide that scientists have been tracking for decades. Every year, millions of tons of volcanic rock creep seaward at rates between 3 and 5 centimeters, pulled by gravity toward the Ionian Sea below. To most observers, this movement is invisible, but to volcanologists studying Etna, it represents one of the most dangerous geological processes unfolding on the planet today. The entire southeastern sector of the volcano, a massive wedge of unstable terrain extending from the summit craters to the sea floor more than a kilometer below the waves, is slowly detaching from the rest of the mountain. This isn't speculation, it's measurable, documented reality. What scientists didn't know until recently was whether this sliding continued underwater, and if so, what was driving it. For years, the prevailing theory held that pressure from rising magma was pushing the flank outward, like an overinflated balloon straining against its skin. But in 2018, a team of researchers published findings that overturned this assumption entirely. Using an unprecedented network of acoustic sensors deployed on the seafloor off Sicily's eastern coast, they captured something no one had seen before: the underwater portion of Etna's flank moving independently of volcanic activity, driven not by magma, but by the sheer weight of the mountain itself. Gravity, it turns out, is the primary force threatening to pull Mount Etna apart, and that changes everything. Between April 2016 and July 2017, 5 acoustic transponders sat on the Mediterranean seafloor at a depth of 1,200 meters, positioned on either side of a major fault line marking the boundary of Etna's unstable southeastern flank. Every 90 minutes, these devices sent sound waves to one another, measuring the distances between them with sub-centimeter precision. For months, the data showed only gradual, steady movement, the kind of slow creep that scientists expected. Then, in May 2017, something extraordinary happened. Over the course of just 8 days, the transponders recorded a sudden slip of more than 4 centimeters along the underwater fault. On land, GPS stations along the coast registered nearly identical displacements at exactly the same time. This was a revelation. The movement occurred far from Etna's summit craters, in a region where magma pressure should have little influence. It happened during a period of relative volcanic calm, with no major eruptions or intrusions to explain the displacement. And it accelerated and stopped abruptly in a pattern consistent with what geologists call a slow slip event, a type of fault movement more commonly associated with tectonic earthquakes than volcanic flanks. The implications were staggering. If gravity, rather than magma dynamics, is the dominant force driving Etna's flank instability, then the risk of catastrophic collapse is far greater than anyone had previously assumed. Because gravitational sliding doesn't stop when eruptions cease, It continues, relentless and inevitable, until something gives way. Mount Etna has collapsed before. Research suggests that approximately 8,000 years ago, with radiocarbon dating pointing to around 7,500 years before present, during the early Holocene, the eastern flank of the volcano experienced a catastrophic failure. In an event eerily similar to the 1980 eruption of Mount St. Helens, a massive section of the mountain's eastern slope detached and slid into the sea. Based on seafloor surveys and computer modeling, researchers estimate the landslide displaced roughly 6 cubic miles of rock and sediment, enough material to bury the entire island of Manhattan beneath a layer of debris thicker than the Empire State Building is tall. The avalanche appears to have crashed into the Mediterranean at speeds exceeding 200 miles per hour, in the process displacing vast quantities of seawater in the process. What followed was a tsunami of almost unimaginable scale. Computer simulations, reconstructed from seafloor sediment surveys, suggest that waves may have reached heights of up to 130 feet as they radiated outward from Sicily. Within hours, these waves would have slammed into coastlines across the eastern Mediterranean, traveling at speeds approaching 450 miles per hour in the open ocean. Evidence of the disaster has been found in chaotic sediment deposits on the seafloor of the Ionian and Sirte abyssal plains, and in tsunami-related layers discovered in shallow depressions across the region. The waves appear to have reached as far as present-day Israel, where archaeologists have uncovered compelling evidence that a thriving Neolithic village called Atlit Yam was suddenly abandoned around the same time. Excavations revealed piles of gutted fish left to rot, signs that could indicate an abrupt evacuation by people who never returned. The landslide left behind a scar that remains visible to this day: the Valley do Bove, a horseshoe-shaped depression carved into Etna's eastern flank, stretching 5 kilometers wide and more than 1,000 meters deep. For millennia, this vast amphitheater of cliffs and rocky walls has served as a natural basin, channeling lava flows away from populated areas during eruptions. But it also stands as a permanent reminder of what can happen when a volcanic flank becomes too unstable to support its own weight. And now, scientists watching the mountain's current behavior see disturbing parallels.
Today, Mount Etna is one of the most intensively monitored volcanoes on Earth. On land, a dense network of GPS stations, seismographs, and satellite-based radar systems tracks every tremor, every millimeter of ground deformation, every plume of gas escaping from the summit craters. But it's the underwater monitoring that represents the cutting edge of volcanology. Since 2016, researchers have been deploying increasingly sophisticated instruments on the seafloor to measure movements that would be impossible to detect from space. Acoustic transponders communicate with one another continuously, building up detailed records of how the submerged flank shifts over time. Fiber optic cables laid across active fault lines use laser interferometry to detect even microscopic strains in the Earth's crust. Pressure sensors embedded in seafloor sediments monitor changes in temperature and pore pressure that might signal an impending movement. In 2023, an international team returned to the site to upgrade the monitoring network, adding 13 additional geodetic stations and deploying ocean-bottom seismometers to precisely locate underwater earthquakes. The goal is not just to observe, but to understand, to identify the precursory signals that might warn of a catastrophic collapse before it happens. Because right now, despite all this technology, scientists still can't predict when or even if such a collapse will occur. They can only watch, measure, and wait. The mechanics of what's happening beneath Etna's southeastern flank are complex, but the basic principle is straightforward. The mountain is too heavy for its foundation. Etna sits on a sloping basement of sedimentary rocks that dip toward the Ionian Sea. The eastern side of the volcano, which extends far offshore, lacks the underlying support present on its western and northern flanks. Over time, the immense weight of the volcanic edifice, towering 3,400 meters above sea level and rising from below the waves, creates enormous gravitational stress. This stress is concentrated along pre-existing faults and fractures, which act as planes of weakness where the mountain can slide. But gravity alone doesn't fully explain the pattern of movement. Etna's flank doesn't slide continuously at a steady rate. Instead, it moves episodically, and bursts of accelerated motion separated by periods of relative stability. Scientists have documented at least 11 of these slow slip events between 2006 and 2016, each lasting anywhere from 2 to 67 days. During these events, the flank can lurch seaward by several centimeters in a matter of weeks, then settle back into a slower baseline creep. What triggers these episodes remains unclear. Some appear to coincide with volcanic activity, magma intrusions that inflate the mountain and temporarily steepen the slope. Others occur during periods of volcanic quiescence, suggesting that external factors like rainfall, erosion, or tectonic stresses may play a role.
The underwater fault systems are equally complex. The southern boundary of the sliding flank is marked by a right lateral strike-slip fault that extends from the coast all the way to the deep seafloor, more than 20 kilometers offshore. This fault is not a single, simple fracture, but a zone of deformation where multiple structures interact. Near the coast, movement is distributed across several smaller faults. Farther out to sea, these merge into a single, pronounced feature that shows up clearly in high-resolution seafloor maps. The northern boundary follows a different trajectory, defined by left lateral faults that curve around the Valle del Bove and extend offshore as a series of underwater ridges. Together, these boundaries outline a massive block of unstable terrain that encompasses much of Etna's eastern and southeastern flanks. Volcanic flank collapses are not unique to Etna. They occur at volcanoes worldwide, and their consequences are almost always catastrophic. The most famous recent example is Mount St. Helens in Washington state, where the collapse of the volcano's northern flank on May 18, 1980, triggered the largest debris avalanche on Earth in recorded history. The avalanche, traveling at speeds up to 150 miles per hour, devastated an area of 230 square miles and killed 57 people. But St. Helens is a small volcano compared to Etna, and its collapse occurred on land, limiting the broader regional impact. A more apt comparison might be found in Hawaii, where the island volcanoes of Kilauea and Mauna Loa have experienced numerous large-scale collapses over their lifetimes. Underwater surveys of the Hawaiian seafloor have revealed massive debris fields extending hundreds of kilometers from the islands, the remains of ancient landslides that reshaped entire sections of the ocean basin. Some of these collapses generated tsunamis that crossed the Pacific, leaving deposits on distant shores. Unlike St. Helens, Hawaii's volcanoes slide gradually, in a process similar to what's happening at Etna today. But the Hawaiian flanks are also smaller, and they collapse into the deep Pacific, where the tsunami energy can dissipate over vast distances. Etna's situation is uniquely dangerous because of where it sits, on the edge of a confined sea surrounded by densely populated coastlines. The eastern Mediterranean is not the open Pacific. Tsunami waves here have nowhere to dissipate. They bounce off coastlines, amplify in shallow bays, and converge on population centers with devastating force. 1 million people live in the metropolitan area of Catania alone, less than 25 miles from Etna's summit. Tens of millions more inhabit the coasts of Greece, Turkey, Egypt, Libya, and the Levant, all within reach of waves generated by a major Etna collapse. The scale of such a disaster is difficult to comprehend. If a section of Etna's flank, comparable in size to the ancient Valle del Bove collapse, were to fail today, the resulting tsunami could dwarf anything seen in the Mediterranean in recorded history. Based on what scientists understand from past collapses and modern modeling, waves reaching heights of tens of meters would likely strike the Sicilian coast within minutes, giving residents almost no time to evacuate. Within an hour, the waves would reach the Greek islands and the coasts of North Africa. Within 2 to 3 hours, they would arrive in Egypt, Israel, Lebanon, and southern Turkey. Low-lying coastal cities, ports, and tourist resorts would be inundated. The economic damage would run into the hundreds of billions. The loss of life could be staggering.
Yet despite the clear and present danger, scientists remain unable to predict when such a collapse might occur. The problem is one of timescales. Volcanic processes unfold over geologic time, thousands, tens of thousands, even hundreds of thousands of years. Etna itself is 500,000 years old. The Valle del Bove collapse happened roughly 7,500 to 8,000 years ago. The current episode of flank instability has been ongoing for at least several decades, possibly much longer. Against this backdrop, human lifespans are vanishingly brief. A collapse that is imminent in geologic terms could still be centuries or millennia away in human terms. Or it could happen tomorrow.
What scientists do know is that the southeastern flank appears to be moving faster than it has in the past. Geodetic measurements show that displacement rates have increased over the last few decades, though whether this represents a short-term fluctuation or the beginning of an accelerating trend remains uncertain. They also know that the flank's movement is not uniform. Different sections slide at different rates, creating internal stresses that could eventually trigger a larger failure. And they know that the underwater portion of the flank is just as unstable as the part above sea level, a finding that only emerged in the last decade, fundamentally altering the risk assessment. What they don't know is what precursory signals might warn of an imminent collapse. Will there be a sudden increase in seismic activity, a dramatic acceleration in the rate of sliding, changes in gas emissions or thermal output from the volcano? Or will the collapse come with little or no warning, as it did at Mount St. Helens, where the catastrophic flank failure was triggered by a single earthquake striking a critically unstable slope? These remain open questions driving the current monitoring efforts. Every new sensor deployed, every additional data point collected, brings scientists closer to understanding the mountain's behavior. But gaps remain, critical gaps. Mount Etna is a study in contradictions. It is Europe's most beloved volcano, a UNESCO World Heritage Site, a source of wonder and fascination for millions of visitors who come each year to witness its fiery displays. It is also one of the planet's most dangerous geological features, a ticking clock whose countdown no one can read. The people who live on its flanks know this duality intimately. They have learned to read the mountain's moods, to sense when the ground trembles with menace and when it merely sighs with the restless energy of the earth below. For them, Etna is not an enemy, but a fact of life, as familiar and ever-present as the sea. But familiarity breeds complacency, and complacency is a luxury that may no longer be affordable. The June 2nd eruption was a reminder of how quickly conditions can change, how a routine day on the mountain can turn deadly in moments. The collapse of the southeast crater, though relatively small, demonstrated the same basic principle that governs the behavior of the entire southeastern flank. When rock becomes too weak to support its own weight, it fails, sometimes gradually, sometimes all at once. Scientists studying Etna are not predicting imminent catastrophe. They are, however, sounding a note of caution that grows louder with each passing year. The southeastern flank is moving. It is driven by forces that do not rest, that cannot be stopped, that accumulate stress over timescales invisible to human perception. One day, whether in our lifetimes or our grandchildren's or 100 generations from now, that stress will exceed the strength of the rock holding the mountain together. And when it does, the consequences will reshape not just Etna, but the entire region it overlooks. Until that day arrives, the watching continues. The sensors record, the data accumulates, and the mountain, ancient and patient, keeps its secrets. If this story left you thinking about the forces shaping our planet, subscribe to stay informed about the geological events unfolding around us. Because the Earth is always moving beneath our feet, and sometimes it's closer to breaking than we realize.